Hey everyone, welcome to another one of our live sessions here at the World Science Festival. A continuation of what initially began as your daily equation, World Science U, World Science Festival, all blended together. Today, we'll do the usual, have some Q&A for a little while, and then we're gonna have a conversation with a guest. Many of you know it's the Nobel laureate, Barish, Nobel laureate whose contributions made the first detection of gravitational waves possible. So it's really exciting to talk to Barry. I also wanted to note something that I've seen in, I don't study the comments, be clear. I just sort of glance at them on occasion, but in the comments or the chat or somewhere, I saw a number of people when we were talking about black holes. Obviously, we're talking about that because of the recent announcements of the Nobel Prize in Physics, highly associated with black holes, you know, on the theoretical side, on the observational side. But there are a number of comments that said black holes are nonsense. This is silliness. You know, these scientists are talking about something that's just a fantasy, a fiction. And normally when I see that kind of stuff, I'm like, yeah, whatever. And I'm pretty much that way here too. But what's missing in that way of looking at things, especially if someone doesn't know the true scientific background of the story, is that there was a time when that might have been a reasonable perspective. But the success story of black holes is one that we hold up as a paradigm of how we theorists envision our understanding of the universe progressing. Because look, let me just quickly take you through it. Many of you are familiar with these ideas, but whatever, let's just go through it. 1915, Albert Einstein writes down the field equations of the general theory of relativity. A couple years later, Karl Schwarzschild gets a hold of the manuscript, finds the first exact solution of Einstein's field equations. Einstein himself only had found approximate solutions to the field equations, okay? So that's a great achievement in its own right. But within the so-called Schwarzschild solution, you can see the possibility of black holes. You can see that if matter is crushed down to a sufficiently small size, then the indentation in the fabric of space will be so significant that nothing will be able to resist falling down that indentation. And by nothing, I really mean nothing. Nothing also includes beams of light, photons. And if photons can't climb out of this gravitational well, then the region goes dark. Okay, that was all theoretical, right? Now, Einstein himself, at that time, would have made a comment if YouTube existed, right? Or if these kinds of sessions existed. Einstein, if he deigned to participate, I don't think he would have, but he would have put a comment, something along the lines of, yeah, sure, the math says they exist, but these mathematically oriented scientists are taking my mathematical equation, a Schwarzschild solution to that mathematical equation, they're taking it to an extreme that doesn't exist in the real world. In fact, Einstein himself wrote papers where he tried to establish that black holes would not be real. They weren't called black holes then, but this solution being pushed to that limit where you have gravitational implosion, gravitational collapse, Einstein didn't think this would actually be real in the universe. This is Einstein saying that, okay? So again, that resonates with the comments that I see on YouTube or in wherever I was seeing those comments. Okay, good. Now, but that was the 1930s and 1940s. It was a long time ago. In the interim, people came up with mechanisms by which gravitational collapse would happen. Stars use up their nuclear fuel. They can't support their mass. They implode inward, okay? But beyond these abstract theoretical ideas, there are also observations that began to take place, right? So the Nobel Prize was awarded for observations of stars going around the center of our Milky Way galaxy and being whipped around at such incredibly high speeds that the only candidate for what could exert the powerful gravitational pull causing those stars to whip around the center of the galaxy is an incredibly massive black hole. In fact, I think we may have a visual. If we can bring up the visual of stars going around the center of our Milky Way galaxy, yeah, there you go, right? So here's the analysis. You measure the motion of stars, and you find that those stars, you can sort of see it here, they're being whipped around, right? The center of our Milky Way galaxy. Then you look closely to see what is whipping them around, and it's just so compact. It's so dense. It's so small, yet exerting such a powerful gravitational pull that it pretty much has to be a black hole. Good. Okay, so that is what was awarded the Nobel Prize. But even beyond that, we have the Event Horizon Telescope data, right? Can we bring up the image of what the event, there's a black hole, right? Galaxy M87, 55 million light years away. This is a black hole whose light, not from within the hole, but from the exterior of the hole, gas that surrounds the hole, heats up, emits radiation. But, that's pretty much the most straightforward demonstration that these ideas are borne out in the world. Now, look, let me also emphasize, we don't know everything about black holes. Black holes are the theorist's laboratory par excellence, right? That is the domain in which we push our understanding to the limit. And our understanding of black holes is today in flux. There are questions about black holes that we don't fully know the answer to. We don't fully understand necessarily what happens at the event horizon, at the edge of a black hole. We certainly do not know what happens at the center of a black hole. But that's the nature of research. You make theoretical headway, observation confirms your ideas and then subjects them to further scrutiny. You make further theoretical advances and on the chain of reasoning goes. So I'm not saying that Einstein's version of black holes, perhaps I shouldn't attribute it to Einstein, Einstein's equations, the version of black hole that comes out of Einstein's equations, we're still in the process of fully understanding what this monstrous beast actually is. But there can be no doubt that something very close to what we call a black hole, very close to the phenomenon, the features that we talk about, there's a version of something like that out there in the world. It is no longer science fiction. No longer can a rational person not entertain this very real quality of the world. And what we'll be talking to Barry Barish about today is other evidence for black holes, an indirect signature coming from black holes that are in binary pairs and orbiting each other and colliding and creating ripples in the fabric of space, gravitational waves. Another independent piece of evidence that these ideas are correct. So again, I know that in some sense I'm preaching to the converted here. Most of you are not skeptical in the way that some in the comments section are. And I love skepticism, don't get me wrong. But skepticism has to be brought up to be commensurate with what we know, or else it's just plain old ignorance. I don't mean that in a derogatory sense, but to say things like I see written in the comments is ignorant. Okay, it's not being an iconoclast. It's not somehow being anti-establishment. It's just being plain silly. And we see that kind of silliness playing out on the world stage a lot. So when I see it happen here, I just, on occasion, feel the need to call it out. All right, so I hope that wasn't too much of a rant for you guys. If I was going to rant further, it's something else I'd rant on. In fact, I'm going to rant on it for 30 seconds. There was another person who noted how in the conversation last week with Nobel laureate Harold Varmus, we spent a lot of time talking about the coronavirus and the pandemic. And somebody wrote in and said, hey, it was really interesting conversation, but it was kind of discordant. Maybe that's my word or theirs, I don't recall. A little discordant to hear you talking about the pandemic, which you have diligently avoided talking about for 7 months. And oh, sorry, my phone is ringing. Just sort of ignore that. But the point is, I didn't diligently avoid the pandemic for 7 months. That's not at all the case. In fact, if you go back and look at the first installment of your daily equation, I said there the reason why we're starting the series is so that those of you who are completely wrapped up with the pandemic might have something else to distract you, might have an outlet to think about things that perhaps are a little transcendent relative to the difficult times that we are experiencing here as a species on planet Earth. And so the point of not dwelling on the pandemic in these sessions and your daily equation and so forth was not to avoid it. Rather, it was to provide a respite from it, which is a very different motivation. So anybody, you want to talk about the pandemic, bring it up in the question session. Many of us, though, enjoy talking about the larger issues of space, time, gravity, black holes, and so forth. And that's the reason why the pandemic hasn't had a major footprint until last week in our conversation. We weren't avoiding it. It was just a choice to let the mind free itself from the troubles and travails that we experience on a moment-to-moment basis and fly out to the cosmos. Anyway, okay, with that out of the way, let's now look at some of the questions, and at about 3:30 or so, we will bring in Barish. Although I just realized something, I had to move my computer because the lighting was so bad with the sun coming in, and I am down to 13%, 10%. And I'm going to take half a second here, guys, to try and find a power cord. And this is going to require that I get up and move around a little bit. So don't go anywhere. This is this last minute change that we made. And the one wire that we forgot to move and plug in is the power. Got the internet, got the microphone, got everything of that sort. So hang on half a second. I'll be right back. All right, power cord. Where are you? All right, I got the power cord. Sorry about that. We are usually far better prepared, but the sun made an unexpected appearance. It was overcast, and then the sun decided to come in and spoil the beautiful setup that we had. So I had to move, and let me just see if I can figure out how to plug a plug in real time with you all watching me. Okay, that is good. And with this, we should be all set. All right. With any luck, we'll hear that wonderful little ding. Oh, God, just barely did it with 2% to go. I hope I do not lose you guys. I'm going to take down power and everything else to try to make it build back up. Okay, good. All right. Sorry for that little kerfuffle there, but let's take a look at what the questions have here. Okay. Gilot asks, can entanglement measure two spin components? So when you have an entangled pair of particles, their spins are correlated with one another. And so when you measure the component of the spin of one particle over here, say find it spinning up, you measure effectively the other component must be spinning down if they're in a so-called spin zero state where they're anti-correlated against one another. But you can't measure incompatible observables. You can't measure components of the spin that are mutually incompatible in the sense that their observables don't commute with one another. And so you can't somehow do an end run around the dictate of quantum mechanics. So there are certain qualities of the world that you can't know simultaneously. So the uncertainty principle, we normally think about it as saying that you can't know the position and the speed, the position and the momentum of a particle simultaneously. But it also tells us that you can't know the X component and the Y component of a spin simultaneously either. Incompatible observables. They don't commute with one another. So you can't, if that was the point of the question, no, you cannot end run around that kind of quantum uncertainty. The knowledge asks, when will our sun become a black hole? Answer to that is it's likely, more than certain, that our sun will never become a black hole, in the sense that the life cycle of a star whose mass is comparable to that of our sun involves the sun ultimately using up all of its hydrogen, transitioning to helium. The sun will swell and so on. It will become a couple hundred times its current size in the process. It'll then fall back down. It'll use its helium for as long as it can. But ultimately, our sun will transition into a white dwarf. It will not have the process by which it would turn into a black hole. It needs to be heavier. So if the sun was, say, 10 times its current mass, then the likely scenario for the life cycle would indeed involve the sun undergoing a kind of supernova explosion toward the end of its life, blowing out of its surface, and the remaining core would not have any ability to withstand the remaining residual mass, and that would collapse all the way down into a black hole. So it's not that every star turns into a black hole at the end of its life. Many will, but it depends sensitively on the mass of the object. Now, if you're willing to wait even longer than, say, the life cycle of a star, in the end, all matter we anticipate being sucked into black holes, and I'm now talking about not on the order of billions of years, but I'm on the order of 10 to the 100 years, 10 to the 200 years. If you're willing to talk about those timescales, then you can imagine that our sun falls into a black hole, and that way becomes part of a black hole. But I suspect that was not the intent of the question. All right, guys, I am worried here that I am at 1% power. Let's hope that I do not go down to 0, which is an unfortunate number when you're looking at the residual power on your screen. I wonder if I'm having an electrical issue. If I go away, I'll come back. I'll find another computer. In fact, if someone's listening to this right now who is within walking distance of where I am, maybe having a standby computer that's all powered up would probably be a good thing. But I'm going to assume that somehow these machines are built with an equilibrium that they can build back up or at least stay static without going down further. Okay, so other questions. And again, we're going to bring Barish in about 3:30, but keep your questions coming. What do we have here? Ozgur asks, why is there something rather than nothing? I don't know the answer to that question. Obviously, that's the deepest of all questions, in some sense, deepest of all physics questions. Why is there a universe at all? Leibniz famously asked a version of that question. And we've been struggling to gain insight into it ever since. It's not as though many physicists spend their time in their office thinking about why is there something rather than nothing. Rather, we assume that there's some answer to that question. God, physics, we don't know, quantum mechanics. And then we look at the something and we try to make sense of the something by developing math and equations, observation, experiment to make sense of planets and stars and people and black holes and galaxies and so on. There are ideas, however, speculative though they may be, about why there is something rather than nothing. And quantum mechanics may be key to that. You may be familiar in quantum mechanics, you can have energy eruptions in space where momentarily energy is extracted from the vacuum, say in the form of a electron-positron pair. They then collide, give that energy back to empty space. But there is this kind of eruption of something out of nothing. There's still empty space already, so it's not pure nothingness. But you can imagine a version of that story that might involve our universe emerging from a quantum fluctuation, a quantum eruption. And maybe there's a negative version of our universe, and maybe somehow our universe and that anti-version don't find each other. They don't quickly collide with one another, giving the energy back. So maybe there's kind of a mirror version of our universe balancing us all out, and we still therefore in total have nothing, 0 in total, but 0 has been rewritten as our positive universe and some other negative universe, and that may one day shed light on why there's something rather than nothing. But my first answer is the most honest, accurate answer that anybody can give today, which is, why is there something rather than nothing from the standpoint of fundamental physics? Answer, we do not know. Okay, back to some questions over here. Oh, good. I'm at 5% power. All right. I'm a little less concerned. The vector's heading in the right direction. Tar says, physicist Sean Carroll, a friend of mine, has been complaining about how the physics community is avoiding to indulge in understanding the true nature of quantum mechanics and are just happy with the results. Your views. I share Sean's perspective on that. I, too, am among, I think, a minority of physicists. And I can't tell you the percentages, right? I haven't done any polling. But just through my informal conversations with colleagues, most are less than thrilled to engage with some of the fundamental mysteries of quantum mechanics and are more happy to use quantum mechanics to just figure things out. What are the mysteries that I'm referring to? The mystery of the quantum measurement problem. How does the world transition from the fuzzy nebulous haze of a probability profile that comes out of the wave function of quantum mechanics? How do you transition from that probabilistic haze of many possibilities to the definite reality that we encounter upon observation or measurement of the world? Nobody knows the answer to that, and that's a pretty fundamental question. Other fundamental questions: is the wave function, is the probability wave real? Is it as real as, say, an electromagnetic wave, a gravitational wave, as we'll be talking about? Or is that probability wave, is that wave function simply a mathematical articulation of the best understanding we have of a physical system, but the wave is not really out there undulating in the world? If that wave is real and you're doing, say, standard non-relativistic quantum mechanics that you study, say, in high school or college for some of you, if you're looking at an n-body system in 3 dimensions, then that wave function has 3n plus 1 arguments. 3n plus 1 arguments, which means even the picture of a wave undulating through 3 dimensions of space is just a wrong picture for the non-relativistic wave function. The wave function is undulating through a 3n plus 1, or if you take the time out, just make that a movie of its shape over time, undulating through a 3n dimensional spatial environment. Is there any reality to those 3n dimensions, configuration space, or not? So these are the kinds of questions that people who worry about the foundations of quantum mechanics do think about. I will say this. I wrote a book called Fabric of the Cosmos back in, 2004, I think. Young man back then. God, a long time ago, 16 years ago. Oh, insane. That's a whole nother story. But here's the reason I bring that up. In that book, I took on issues of quantum entanglement and EPR and that sort of stuff. And I do remember colleagues at the time saying, yeah, it's kind of interesting to talk about that, but like, why? Like, why would you spend any time thinking about EPR and entanglement and so forth? And short time later, as theoretical physicists began to grapple more fully with black holes and how black holes interface with quantum mechanics, these issues of entanglement and EPR became central to the kinds of work that we need to do to make progress at the frontier. So certainly that aspect of quantum mechanics has taken hold in the majority of the physics community. I would no longer say that that is a backwater. And in the 80s or 90s, it was definitely a backwater. People weren't focused upon entanglement and Einstein, Podolsky, Rosen. That has largely changed. So the other qualities of quantum mechanics that are still mysterious, I imagine there will come a time when people spend more time thinking about them as well. All right, a couple more questions before we transition over to today's guest conversation. Let me see if something catches my eye over here. Pretom asks, sir, can Mars be made habitable in our lifetime? It depends what you mean by habitable. Can we make regions of the planet conducive to our form of life by building structures that allow us to survive within them? Yeah, they're on the table. In fact, you can search online. There's some clever ideas that have been developed, and no doubt that some of these can work in our lifetime. If you're talking about terraforming Mars and turning Mars into the new Garden of Eden, that I don't anticipate happening in our lifetime. Okay, let's do, I still have a couple minutes. I'd like to start at 3:30 with our next phase of our conversation here. Let me just, all right, what do we have? Serena Shao, is it possible for a human to live near a black hole, perhaps in a type 2 civilization? You know, it's funny, the type 1, type 2 civilizations, I never really got into that categorization scheme. It has to do with, I guess, the kinds of energy sources that civilization has conquered. So maybe what is type 2 has conquered solar system level or galactic. Somebody can tell me. I don't have that categorization. Why am I having trouble with that word in mind? But can a person live near a black hole? Yeah. In fact, we could be living near one right now, in the sense that if there's a huge black hole, then its event horizon is far away from its center. If you recall, and I mentioned Schwarzschild's solution, and sometimes we talk a little math here. What is the radius of a black hole of mass m? By radius, I mean, what is the value of the Schwarzschild parameter r? And the answer is 2gm over c squared, twice Newton's constant times the mass divided by the speed of light squared. And so if you have an ever greater mass black hole, r, which is linearly proportional to m, will just get bigger and bigger. It also turns out that the curvature near the edge, the event horizon of the black hole, gets smaller and smaller the bigger the black hole gets. So the forces that you feel near the edge of a black hole, in some sense, become ever smaller as that black hole gets ever bigger. And so if you have a big enough black hole, you might be hovering right near the edge and not even know it. In fact, we could have all just crossed over the edge of a black hole, and we wouldn't necessarily know it either if that black hole was sufficiently large. So yeah, in principle. Now, as the black hole gets smaller and smaller, it's more of a challenge. The acceleration that you have to constantly apply to stay outside that black hole becomes ever more intense. But there's nothing in principle that says that you can't live outside the edge of a black hole. And of course, if you're far away from the edge, then we're all living outside the edge of a black hole. All right. Sam asks, Professor Greene, how are particle pairs still entangled when one member of the pair is sucked into a black hole? How can they still be communicating? Well, yeah, Sam, good. That is the kind of question that people have been struggling with a lot in recent years. Because you're right, if you have a pair of entangled particles, spinning up and spinning down is the canonical example that we often use. If you have this pair of particles that are entangled in this way, you separate them. We've discussed in previous gatherings how there can be a kind of quantum thread that stitches these two particles together, making them act as one, even though they're widely separated, such that, for instance, if you measure one of these particles, you find it up, the distant particle immediately snaps out of that fuzzy quantum haze and points down instantaneously, even though you didn't do anything to it. So that's traditional entanglement. What happens to entanglement in the vicinity of a black hole? And in particular, if one member of the entangled pair falls in and the other rushes away, how does that affect the entanglement? Now, according to the most straightforward, vanilla interpretation of Schwarzschild's solution to the Einstein field equations, the entanglement should persist. Why? The edge of a black hole, as I've emphasized, is not a place in space where anything happens. There's no signpost that says you are now at the edge of the black hole. It is an ordinary location in space, which has the unusual feature that you then can't turn around and exit the region to which you entered, but you don't feel anything. It's not like the bars go down and you're locked in. So because nothing happens at the edge of a black hole, nothing singular happens at the event horizon of a black hole, the belief was the entanglement just persists, period. Now, for reasons that would take me a little far afield to describe, more recently, as people have thought that through further and wondered about the radiation, the Hawking radiation that comes out of a black hole, and the entanglement that that yields, and the kind of entanglement that that radiation must be subject to carry away the information within a black hole. When these considerations are thought through carefully, some have concluded that the particle inside the black hole and outside the black hole, the entanglement is destroyed. The entanglement is lost. And if that's the case, it's as if the event horizon kind of snaps the thread of quantum entanglement uniting the two particles, one inside, one outside. And when you snap that thread of quantum entanglement, it generates energy. Now imagine many particles all over the edge of a black hole, some inside, some outside, all entangled. If all of their lines of entanglement are snapped, there's a lot of energy along the event horizon of the black hole. So much energy that the temperature is huge and the conditions are extreme. And that is what has given rise to the name firewall for the event horizon of a black hole. The proposal, not universally agreed upon, that the edge of a black hole might actually be a real location in space. There is a signpost there. The signpost is a firewall of intense heat that when you go toward the edge of the black hole, you are incinerated. So the snapping of the lines of quantum entanglement that Sam asks about may be the origin of a new way of thinking about black holes, where the edge of a black hole is a firewall. Okay, good question. With that, let's, the warm-up act, if you will, let's turn to the main event, which I'm looking forward to enormously, which is a conversation that I'll now have with Barry Barish. Let me give a little introduction before bringing him in. Barry won the Nobel Prize in 2017 for his work on LIGO, Laser Interferometer Gravitational Wave Observatory. We'll talk some about that. He was a principal investigator for LIGO, 1994. Its director from 1997 to 2005. And he is credited with making substantial contributions to this incredible scientific achievement of detecting the first ever gravitational wave rippling through the fabric of space. So with that, let me bring Barry into our discussion here. Barry, how are you doing?
Good. How are you?
Great to see you.
Yeah, good to see you too.
Was the last time I saw you, was it at the World Science Festival in New York, or was it in Tenerife? I can't remember which happened.
I think Tenerife was after.
Tenerife was after. Yeah. Okay, great. Yeah. So I remember that was a fun meeting out there.
Yeah, it was.
A beautiful environment. Now we can only dream of being in places like that. So where are you now? You're somewhere in California, presumably?
We live in Santa Monica, and I'm
Santa Monica.
100 meters from the beach here.
Oh, that's nice. Yeah, good.
It's maybe 80 some degrees today, so it's nice.
Yeah, it's a little warm here too. Usually it's freezing up here in upstate New York, but we're having a momentary spate of warm weather, which is kind of nice. So, I just would love to talk about, obviously, the detection of gravitational waves and what's happening now to bring people up to speed on what's happening. But before we do that, if you don't mind, just a little bit of background on you. Our audience loves to learn about the journey that these great scientists such as yourself have been on. And last week we spoke with another Nobel laureate, Harold Varmus. I don't know if you know Harold.
Yeah, I do.
I think all you Nobel laureates, you probably all know each other, right? I mean,
well, not only that, we may be like second cousins. Barish is a family name of his in his family, but we're not sure how to connect it. But
that's interesting. But the reason I bring him up, I didn't know that connection, but the reason I bring it up is, Harold began interested in literature and in reading and in writing, and only much later on transitioned into science. And I think I read or heard that you also had an interest of a similar sort. So you weren't like a math, chemistry, physics kid from 5 years old.
No. I came from a family where neither parents went to college, so I didn't have much, and we also didn't have much money. So I just was a public school kid with very little guidance anywhere. Are you still there?
Yep, sure I am. Yep.
No, oh, I see. It just shows me.
Yeah.
Anyway, but when I was a kid, I liked to read a lot. And I grew up here in Southern California, not so far from Hollywood. And of course, in Hollywood, storytelling's a big deal.
Yeah.
And so I like to read, and I like storytelling. And so I was attracted to words more than science. Although as a kid, I was good at it and won some math contests and stuff, but it really wasn't my interest. And I discovered, and then I was the editor of the school newspaper, so I like to write and read and all this. And then, so I thought when I was about 13 or so, I discovered good literature and, read the Russian novels and things like that. And I thought I'd be a novelist. That was my goal at 14 or 15. And that got cured by a high school English teacher, my first real class in literature. And she assigned a book. You can maybe guess at the book as I introduce it, which managed to cure me from literature. And it was the wrong book to give to this 15-year-old. I don't know about another one, but to me. And I read this book and decided I should do something else with my life. I wasn't sure.
Are you going to tell us? Are you going to tell us what the book was?
Yeah, I'm going to tell you. I was just giving you a minute to. Yeah. So anyway, the book was Moby Dick.
Ah.
Now, I don't know if you've read Moby Dick.
Yeah. So wait, you were 15, you said?
Yeah.
So I was given Moby Dick as a 7th grader, which
that's even younger. Well, maybe you were more sophisticated than me.
No, I had trouble.
I had absolutely no sense of what a metaphor was at that age. Okay.
Yeah.
Moby Dick is one big metaphor. That's all it is. And so I read this book, and there was a big chapter on the great white whale, which is very important once you understand the book. But to me, it was like the most boring thing I could possibly imagine because the whole thing was over my head. So anyway, because later I read it later, sometime after college, and I enjoyed it a lot. It's great literature. So it was me. It was the wrong book for a 15-year-old. Yeah. And maybe it was for you too at 14 or 15, but it would have cured you from being a writer too, probably. And so basically that made me wander in another direction. And I decided to become that I had to figure out how to make a living and stuff. So I was going to become an engineering student.
Right.
And I was almost the last class. I don't know why they had them in Los Angeles public schools. They had a winter graduating class. Which is unusual, and I was, my horizon didn't go as far as the East Coast. I just kind of saw. So Caltech was one of my interests, also Stanford, but they only took classes in September. So I applied for the engineering school at UCLA and Berkeley.
I see.
And I went to Berkeley. I was an engineering student for 1 semester. But I took freshman physics, and at that time in Berkeley, they were discovering all the elementary particles up at the radiation lab. And Owen Chamberlain, who discovered the antiproton, was my advisor once I switched to physics. And it was just the romance of discovery and so forth. They got me started in physics. I changed to physics, and then the rest.
So do you have a half-written novel sitting in a shoebox?
The other thing, I always thought that physicists can't do physics forever, although I keep trying, and so I was going to come back to trying to write when I got older, but I keep doing physics instead.
Well, it's good for
like to write.
Keep doing physics, yeah. So you were one of the leaders of the Superconducting Super Collider, right? Back in the 90s, which I think most people who are watching this know what that was. This big, powerful accelerator that was going to be built down in Texas. How disappointing was it when that was shuttered? And how surprising was it to you that after the amount of work that had been done, in fact, you can tell us how far had things gone that funding was
altogether about 15 or 20% of $10 billion had been spent. So they had dug a lot of underground tunneling and a certain amount of a campus that was going to be there. So that's a significant investment. I was on the experimental side. A physicist. I was a co-director of one of the two project physics experiments that was going to be done there. I was completely determined to detect the Higgs boson as the first thing, and so we tried hard to make a detector that had the ability to see the Higgs to 2 gamma, which was the process that we thought was the most likely.
Yep.
At that time, and that required a certain amount of technology development, which has ended up in the LHC experiments, to make a thin enough volume where you can actually detect the gamma rays, because otherwise you get them all mixed up with the charged particles.
Yeah. And so were you surprised in whatever year it was?
So I was a little bit, so I wasn't an employee of the SSC itself, but I had actually recruited a lot of scientists to work with us that got employed by the SSC. I was at Caltech still, and I was just commuting back and forth to Texas.
Yeah.
I didn't think it would actually get closed down, but it was threatened to be closed down. It was a new Congress, and I wish I could say I had the insight and so forth, but I didn't. You know,
Yeah.
It was in October of '93 that it got closed, and we weren't prepared for it. I mean, there was a lot of talk about it.
Now, I know there were hearings, and I believe Steven Weinberg spoke at a hearing and others as well. In the end, do you think that physicists could have, was it our fault as a community for not getting enough public excitement behind these ideas back then? Was that, or was it destined to be shuttered no matter what?
Well, I think, I don't think it was the cost. I think it's more what you say, because this was a new conservative Congress, and they were determined to demonstrate they were turning off something. And it was either the space station or this. Of course, the space station was more expensive. It ends up being much, much more. But at that time, it was well known it was more expensive. So it wasn't because of that. NASA had more connections with industry and powerful people. That helped. But I think we failed to make the story that fundamental science needed to be supported and all the right reasons. So I think it.
Now, shortly thereafter, I guess. I mean, what was the time interval that you were able to shift over?
Yeah. So I had Caltech is a zero growth institution. You know, we're the same size as when I came.
Right.
That was my first job, and so we have this feature that when you have a physics department or any department, and you want to stay at the forefront, how do you evolve it when everybody wants to replace themselves when they retire or leave? And it's very hard to kind of evolve with the science. And Caltech, I don't know, I can't say there's a magic formula, but there's a lot of effort in trying to make every single faculty appointment the best faculty appointment you can make, independent of kind of specialty, because of the zero growth. Because of that, I was involved. I started the same year on the faculty as Kip Thorne, and we were good friends.
Yeah.
And I suppose he had convinced me that it was the time for us to get an experimental effort, not for me, but at Caltech in gravitational waves.
Yeah.
And so we failed at the beginning, but then we got an experiment, got approval. The next appointment when somebody left would be in gravitational waves, and maybe 2 appointments. And that started it. And then because the project was big for a little place like Caltech, I then served on a oversight group that tried to handle the fact that how is Caltech going to handle such a big, expensive endeavor as this. And also I was very sympathetic with the goals. I thought originally I didn't think things could be done, because the original idea was to use a big bar that was used. And I always thought that was a bad idea as an experimentalist, because if you have a big bar of aluminum or whatever it is, you hit it with a hammer and it rings at a particular frequency. And that's where it's sensitive. You get that frequency. But who says that the gravitational waves you're going to find are going to be, at that frequency?
Yeah, that's what Joe Weber was trying to do, I guess.
That's what Joe Weber was trying to do.
Right.
No, there's a good picture of him. Yeah.
But Bear, I'm just wondering. So when you began to think about switching over, did you have to like quickly run to Meissner, Thorne, and Wheeler, or like did you already have the knowledge?
I did. I took general relativity as a student. I was always interested in this problem.
Yeah.
And so, but when it changed, so I knew about it. What I didn't know was how realistic, and I don't think anybody really knew very well, but coming out of particle physics where you can predict pretty well, the fact that whether you could predict the sources and rates and so forth was pretty fuzzy, I must say. The only observations were a few binary neutron stars in our own galaxy.
Right.
No black hole. There's no there. So it was really a stretch to think that you're going to spend years building something and know what the sensitivity targets were. So we zeroed in on the only one we could predict at all, which was the binary neutron star system, and that ended up being what our goal was. It turned out that the black hole binaries were a little bit more prolific than that in terms of our ability. We didn't have quite the sensitivity.
Right. So when you started in on this, like I can understand like finding the Higgs. The mindset of the community was the Higgs exists.
Right.
We just got to find it, right? It's the final particle of the standard model. It all works. It's got to be there. But with gravitational waves, there was a sense in the community that sure, they're real, but there are many who felt we will never be able to detect them. So this is a different mindset as opposed to just a shift of field, right?
Well, in terms of what you said, whether they'd exist, I think by the time certainly I got involved, people thought they were. Einstein had trouble whether he believed it or not.
Had trouble, yeah.
Yeah, for a long time, and it was.
Yeah, he wrote papers back in 1916, 1918, which were.
Those were okay. He wrote a paper in the 1930s when he returned to the country.
Refute, yes, exactly.
Where his original title was "Do Gravitational Waves Exist?"
Yeah,
and that's 20 years after, 15 years after he had predicted them. Is a kind of strange paper.
Right.
But the problem was when he submitted that paper, in general relativity, as you well know, it's easy to get these coordinate singularities.
Yep.
You have to really set up the problem right to avoid those. And so he worried that what he was getting was technical and not real. And that got straightened out. For that paper, he renamed it, and he had a war with Physical Review because he didn't want it refereed. That's a story, but then I think most people for the community think it was a meeting in Chapel Hill, North Carolina, after Einstein died in 1958, where the community finally believed. This is the GR community, general relativity community, not the broader physics, believed that they really existed. There was a nice derivation from first principles, and Feynman was at that meeting. And I don't know, you've probably heard of the sticky bead argument. Yeah. So that's where he made that argument, the sticky bead argument, which is basically the argument that in his mind, that if gravitational waves exist, they have to be able to transfer energy. And this was his picture, at least in a Gedanken way, that they could transfer energy. And was also, I think, the stimulus for the bar, because the sticky bead was a rod with rings on it, much like the bar. So
right.
After that meeting, so it didn't take us 100 years as experimentalists. It took us half that because the theorists screwed around for 50 years, almost. And then the problem became an experimental one, and I liked the problem from the beginning. I mean, I thought it was the kind of thing that I would like to do, so I liked it. But as I said, I didn't like the idea. The bars to me seemed like a bad approach. I didn't have an alternate myself. But then when
was the alternate? When was the interferometer idea first?
The first record of it was actually, not surprisingly, in JETP, the Russian journal, which had a little short article, no detailed calculations in the early 60s for interferometry. And later in the 60s, actually, Weber a student of Weber built first interferometer, a test interferometer in his lab. It was kind of empirical. And almost the same period, Ray Weiss, my colleague, was teaching general relativity at MIT and kind of made an exercise for the students to see what kind of detector would be needed. And that's turned out to be kind of a unpublished classical first write down, but I was familiar with that. That turned many of us toward interferometry, and we talked about starting a group at Caltech. It was to work on interferometry, not bars. Bars were getting better and better because experimentalists are clever, and they kept making them colder. And so if you make it cold, it's quieter. We're trying to do that now with the interferometers.
When was the first version of LIGO built? That was...
Well, there were test interferometers, never with the idea that you could measure gravitational waves, but learn how to do the interferometry.
Right.
Because interferometry, if I pick a number, we all saw an interferometer sometime in a freshman lab or somewhere, and you see these fringes, and maybe you could differentiate them to a part in 100 or a part in 50 or something. Yeah. And the good interferometers that people have, technically maybe a part in 1,000 or a part in 10,000. We had to do a part in 10 to the 12th when you put the numbers in. Right. And so that required a really lot of advancements in how to do interferometry itself. Have enough photons, but have enough optical advances that you could do interferometry at the level of 1 part in 10 to the 12th the wavelength of the light.
Right. But at some point, you felt that you understood it well enough that there was a chance that this could work.
Yeah. So if you took at the time I got in, but I was helping oversee it at Caltech before that. The time I got in, we were within, with the tests that had been done on test interferometers, this factor of 10 to the 12th was aimed at doing the neutron star binary where we had some numbers. Yep. And we were within a factor of 100 of that, and there was nothing technically that limited us. So it looked possible with more developments. Right. That you could do it at that point. So I thought it was an experimental. And today, even what limits us is technical problems, not science.
Right. In terms of shielding and things.
No, in terms of the future. So if you ask what's the future of this thing, if you talk about making doing better than the Higgs at CERN, you're limited by physics. The problem is the Higgs is this little bump on top of physics. So you have to know the physics. You can only know it so well. So if you want to see if the Higgs has a partner, there is a problem that you're limited. You can't see it if it's below the background signals, for example. Here we don't have that. The background is physical background. It's not physics. And so what limits us now just doesn't have anything to do with science. So even though we can only detect, distances down to 10 to the minus 22 centimeters, which is pretty small, you can do better. And I can say easily you could do better if you could cool the whole apparatus immediately, or that you change the optics and put a more powerful laser in, or different things. You have to learn how to do those things, but they're technical. So if you look at the future for gravitational waves, it's going to really evolve. First ourselves over the next few years, but it's not limited. It's limited in the sense that we have these big detectors. Maybe somebody will learn how to do an atomic interferometry or something where we can make it smaller. So they're big and expensive, but they're not limited by nature. They're limited by us, basically.
So just to give a little more background to folks who may not be as familiar as some others listening to this. So when a gravitational wave rolls by, what does the mathematics say the signature should be? I think you even have a visual of this, if I'm not mistaken.
Let me see. I did make
slide number 3, maybe.
Slide 2, or start with slide 2 because it shows LIGO.
Yeah, if you can bring that up, that'd be great. Yeah, so slide 2, I guess, is a shot of the observatory itself.
Slide 2 is LIGO. Is it up there?
Yeah, there it is coming up. Okay.
Okay. Yep. So just for reference, people have seen this, but LIGO, those it's shaped like an L. Those 2 arms are 4 kilometers on a side. that means the fundamental 10 to the minus 21 that I talk about becomes 10 to the minus 18, the size of that you have to do. So by making it big, we can have to measure interferometry at the level of the size of the proton, 1,000th of that. The two detectors are identical, very different physical locations. The one on the right is in a swamp and forest and pine forest in Louisiana. And the other one is on the DOE reservation in Hanford, Washington. And they perform the same, as I'll show you in the signature. And those are just interferometers that work like, if we can change to the next slide. Slide 3. Okay, so this is the idea basically, that you want to measure this small number of meters, 10 to the minus 21. And in order to do that, there's two problems that you have to solve, and then you can do it. First, the idea of interferometry. You start with a laser beam on the left, hits a mirror in the center, and you make two arms that are the same length. You split the beam, so half of it goes to the up and half of it to the right. If everything's right, when they come back, if you invert one compared to the other, they'll cancel, and your little photodetector sees nothing. But if they move a little bit, one of them moves a little bit relative to the other one, then they come back out of phase and you see a signal. You see some light, and that's the signal.
Yep.
To do that, as I mentioned, the accuracy is the bottom, in the bottom little insert. That you have to do is 10 to the minus 12 times the wavelength of the light you're doing. That's the technical challenge, and that's really hard. The second problem is that the Earth, we're here on the Earth, we do it on the Earth, we do it where Earth is the quietest, which is basically, we've learned by evolution, that's where our ears work and we can communicate with each other.
Yep.
So we work from 10 to 10,000 hertz, like audio band, even though it has nothing to do with audio.
Right.
But the Earth still, even in that frequency band, shakes much too much for us. And so we have to knock that down by also a factor of, amazingly, a factor of 10 to the 12. But it's just a technical problem. We do it by, and we did it, and it wasn't good enough. That's one of the reasons it took us so long. We do it by just a very fancy version of what's in your car. And that is shock absorbers. Shock absorbers absorb the bump that you go over in your car and then transfer it to lower energy, and it feels smooth. And here we do the same. The Earth shakes, we move it down to lower frequency with just very fancy shock absorbers, and we had 4 layers of it.
These are like suspending the mirror from these pendula that each absorbs some of the shake relative to the next and so on. Yeah,
I think if we go 2 slides forward to slide 5, you can see a picture of it, kind of a schematic of it. And then you'll see if you need the elevator speech for how we experimentally did this, it's on that slide basically. Right. So here's a picture of us making sure we're isolated from the Earth. So it's a big vacuum tank connected to the interferometry, and inside of it is this thing on the bottom is the mirror, and it hangs on a pendulum.
Yep.
The first thing to realize is if I have a pendulum and I hang it, you hang something on, and you move the top, it doesn't move the bottom very much. We all have seen that. Yep. So horizontal motions are taken care of pretty well in a pendulum. And then the vertical ones more in layers of shock absorbers, which are kind of shown over on the left, which is built into the vacuum system. So a combination of this pendulum and these shock absorbers. And that, in effect, got us to an isolation, which was pretty good, but not good enough, of 10 to the 12th. And we achieved that 10 years before we detected gravitational waves. That wasn't good enough. And so what we had to do finally is just steal another silly idea. I mean, shock absorbers are well known. We just did it a little better. The second idea is what you do when you get onto an airplane and you don't like the engine noise. You get one of these earphones, the Bose earphones. You put them in your ears and the engine roar goes away pretty well.
Noise cancellation, yeah.
Yeah, active but the stewardess comes up to you and you still hear her when she asks you whether you want coffee or a drink or something. And so the consistent motion in the back that comes from the engines, you just cancel when it's detected. And so the idea was the same here, that you have to add active isolation that actually has, what we did is build into this thing seismometers. But it's a little harder than the airplane one because we have to tell the direction. So the residual motion that's still there, we have to tell the direction, and we just push back against it and cancel it.
Right.
And that gave us the extra factor of 100 and enabled the detection of gravitational waves.
And the other reason, the fact that you have two of these machines, one in Louisiana, the other in Washington State, is that if there's any kind of crazy shaking that somehow influences the machine, influence one, not the other, you'll be able to at least know that. That's
right. The gravitational wave has to be in the tube within the speed of light.
Right.
And anything else, more or less, is the speed of sound or something else, or won't be in both.
The speed of light, in the sense of the speed of light travel time between the two machines.
Yeah, right.
Right, exactly. So you made these amazing technological advances. You build the machine. For a while, you don't hear anything in the first version of LIGO. You do the upgrade.
The upgrade included a more powerful laser and other things, but the key one was this seismic.
Got it. So then the day happens, September of 2015, right? And so there's this unexpected signal where the two machines twitch, they shake in a manner that looked pretty much the same. The time delay between them, as you say, is the light travel time between them. It's all looking good. But you were presumably not ready to celebrate when you saw that, because it was like too unexpected in a way, right? I mean,
it was even more than that. It was too unexpected and too perfect. We had just turned on, so it was a brand new fixed up detector that had active seismic, fancier laser, all kinds of other things, and we turned it on, and we were in what we call an engineering run, which just indicates that we weren't really settled down yet. And that's when this event came. Different people had different reactions. We're human beings. So there's some people, and they were right, that immediately were ready to celebrate. And others, like myself, for me, it was kind of a nightmare.
Yep. You went out with this, and it turned out that it was a prank, a hoax, a mistake.
Yeah. So there were two possibilities. There were two possibilities, really, and we had to trace down both. One was, we're on the internet and so forth. Is there any way that somebody just inserted this in our data stream somehow? The data comes from the two labs to Caltech and then goes out in the world. It was first observed by a postdoc of ours in Germany. So. And that's a hard thing to trace, because you have to know how clever people might have been to somehow get it there. We had to trace the signals all the way back to their origin to do that. And that took about a month of hard work. And the other problem is, maybe we had done a lot to upgrade the apparatus. Maybe the apparatus can hiccup in some way that it gives you something that you think is a gravitational wave. And so to do that, we have to run and test the apparatus over some period of time to see that it doesn't generate those.
And you could have imagined a coincident hiccup. I mean, something that would have
affected. What we do to check that they couldn't happen is put them out of time with each other and see how many times they would, by statistics, land on top of each other if there was something. And that took about a month of just taking data, and then we were convinced. But as you know, you didn't know about it yet. I think
I heard rumblings,
but and so then and people always ask, how did this big collaboration keep so quiet? The next piece was pretty easy, and that is the idea that we should, telling everybody in the collaboration, the idea that we should figure out what it is first, not just give it out and let other people figure out what it is.
I see.
And that's, as a scientist, you want to do that. You want some time to know what you saw before somebody else does.
Of course.
And that took another month or so. So that got us into November, and then we decided we're going to publish it. And I had been president of the APS at one point, so I was insistent we publish in American, not in Nature or Science. Right. And not in Nature. And so we went to PhysRev Letters, and they had a policy that you could, on exception, make longer than a 3.5-page article. So we called them and asked to make a 10-page article. The reason we wanted 10 pages is that we knew not only did we have to make the case to the critics, our own colleagues that are critics, but this would have enough general interest that we had to write this initial article so that you didn't have to be an expert in gravitational waves to read the article. And that made it pretty challenging.
Right.
We told the PhysRev letters that they agreed, and that we would give it to them by, I think it was November 30th or December 1st. We got together to make the final decision. We wrote it in that time scale. We got together to make the final decision. And then there was haggling. The haggling was over adjectives, basically. Do you declare it a discovery, an observation? It's those kind of words. So it's adjectives, basically. And so it took us another 4 or 5 days to determine that. And we then contacted PhysRev letters and said, okay, it's ready. And they said, whoops, we can't do it now because it's too close to Christmas. This is doing this very fast and secure refereeing. So we said, okay, then we won't give it to you until the first of the year. The reason I tell that part of the story is that on December 26th, we saw our second event. And I just have to say personally, despite all the fall and me thinking that at every level I was convinced, seeing the second event, I had a sigh of relief. There's something about corroborating your result that it looks very different than the first one. But as much as we had convinced ourselves with all the tests, seeing a second event, which we didn't announce to the public for months afterwards, we only announced the first one, but we knew that we had the second one at that point. And at least for me personally, that was the clincher.
So take us through the work that took you through November, as you described it, in terms of figuring out the source. How do you, so you have this twitch. I don't even know if we have the wave form, a still image of the wave form, maybe.
I did the waveform. Let me see.
We may have it somewhere. There we go.
We have the waveform. Oh, there it is. Okay, so this is amazingly, this is essentially raw data. You know, everything you see when you see journals, people have analyzed it. It doesn't look anything like what you see online. This only has a filter to throw away very high and low frequencies outside of our band. That's all that's done to it. Otherwise, it's just the data itself. So that helps you a lot in understanding things. On the left are the two detectors in the top and the center band, and they look alike to the eye. And the bottom one is just putting one on top of the other and sliding it by 6.7 milliseconds, which is within the 10 millisecond speed of light difference between the two sites. And they look to the eye on same as each other.
Yep.
But it shows better on the right. So on the right hand, to see what it is, the top two are the same two traces that are shown on the left. The second line, where there's some more the smooth lines through it, are the calculations from general relativity and we did it for different cases. For the case of the parameters, which I don't give here, of two nearly 30 solar mass black holes colliding. And you can see they look, except being smoother because it's a calculation, they look the same. The trivial way to just see if they are the same and see if anything shows is to subtract one from the other. And that's done in the third frame. And you can see just noise. And that's just the fact that our measurements have noise on them, but there's no pattern or anything that shows. So even without fitting, it gives you a pretty good picture that, you know, the data looks just like Einstein's equations predict.
Yep. So here's my question, Barry, which I know we've discussed on occasion now and then, but I wouldn't mind bringing it up again here. So to do that, if you could leave that graph back up, if you would, to do that middle calculation, the general relativity calculation, requires sophisticated numerical understanding of Einstein's theory. Absolutely. And you guys knew that you'd need that in order to match up the observation with the theory.
Yeah.
But that's a relatively recent breakthrough on the timescales that we're talking about. So you were building LIGO.
Yeah, absolutely.
Without having the ability while you were building it to have done the analysis to figure out if you got a signal, what was the source of the signal. Did that make you nervous for years on end before?
Yeah, well, one of the things that made me nervous, but yes, it made me nervous. And the history of that was we recognized that to the first part of the waveform you can do with just general relativity and post-Newtonian calculations. But when it gets to where the real energy is at near the merger itself, you need to use numerical relativity, which is something that you can't do the calculations by hand. It's too much work. And so you have to do it by computer. And this was the challenge. That challenge was taken up in the 90s at the NSF. They initiated a program called the Grand Challenge, which failed. Basically, numerical relativists, you know better than I suppose, were individuals around different universities. And there wasn't kind of the effort to do that or the technique. And then when that ended at Caltech, we had some money for a visitor program as we were building LIGO, and we brought people that were numerical relativists to work for a while. We also didn't solve the problem then. It was finally solved, as you said, in before we made the detection, but 2006, 2007, something like that. And then it had to be applied. So we didn't have real waveforms that were calculated and applied until not very long before we made the detection. So by some miracle, these things came together at the same time.
Yeah. So it's wonderful that it did. And in fact, the fact that it was the year 2015, 100 years later, a century celebration of Einstein's own discovery of the equations of the general theory of relativity just adds a certain kind of poetry to it all.
Yeah, it makes people who are scientists like you and I kind of wonder about these coincidences that happen. Sometimes.
Yeah, exactly. So that is the first detection of gravitational waves. These two roughly, as you say, 30 solar mass black holes orbiting each other 1.3 billion light years away, colliding, giving off this tidal wave in space that we're able to ultimately detect with the machine that you built. Good. So rightfully, you guys win the Nobel Prize for this. Incredibly exciting. You could stop at that point, but of course, it's too exciting to keep on going. So can you give us a sense of what happened since? I mean, you mentioned a second detection. How many detections do you have in total?
Yeah, I'm going to show you. So let me say a few words and then I'll show you. So interestingly, the discovery itself is important. It's a long thing. And now we can do one whole branch of important work. And that is how much is Einstein's theory of general relativity the right theory of general relativity? There are alternates around. And how well can we test that? And so one branch of what we've been doing since then is to try to test general relativity. We've seen no violations. The simplest test we do is that you can relate to is to add like in electromagnetism, we have the photon, add a graviton, and figure out if it had any mass at all, what it would do to the signal. Yep. And if it had any mass at all, it would add dispersion to the signal. And we can calculate that. And so we basically have put a quite small limit on the mass of a graviton. That's not the best tests, of course. The best tests are to take the parameters of general relativity and compare not just how well they fit Einstein's equations, which we've done so far with our accuracy, but there are alternate theories. And the trouble rate we have right now compared to, say, particle physics as I know it is the alternate theories don't typically aren't developed enough to give us measurements that we can compare. So we can say, yes, it fits Einstein's, but it also fits something else because that's something else. So right now we're in this, I think, not ideal mode where we're looking for violations in Einstein's equation rather than compare differences between different theories because they're just not mature enough.
But like if you look at a Brans-Dicke type theory, adding a scalar field, is that the kind of thing that you
Yeah. So you add that, but we don't have predictions calculated at the level that we can actually compare it in detail with our waveforms.
Got it.
So, the question is if we want to have an alternative that you want to seriously look at, you have to do the work to actually compare it. We haven't done that yet. The other branch which is easier to relate to for everybody except the hardcore physicists who want to look at this, is that this represents a different way of looking at the sky.
Yeah.
We now have the ability to look at gravitational waves from the sky, and not just electromagnetic radiation. And that we've always thought is the real long-term benefit of this whole thing, is that it opens up the possibility of really expanding observational astronomy into a broader realm. And we saw that in the first case when so the black holes, they're not seen. They shouldn't be seen, and they haven't been seen. But then we saw our first case of what we originally thought was the first source we'd see, and that was binary neutron star mergers. And in that case, we actually that actually was seen by many telescopes around the world. We saw it at the same time, within 1.7 microseconds, the same time as 1.7 seconds, the same time as was seen by a high energy gamma ray observatory. And then that gave us enough confidence to inform the astronomers from around the world. They have a way to do that. And roughly half of the astronomical instruments in the world pointed at this and measured it and saw it and measured it in all the different wavelengths.
Half of them in the world, they have that level of
half of the kind of not amateur stuff, but something like there's something like 2,000 identifiable telescopes of some sort or another you can identify, and roughly half of them.
Right, because of course with the initial black hole detection, you didn't even have enough data to pinpoint where on the sky it took place.
And honestly, we couldn't do it here either with two detectors. We needed triangulation.
Yeah,
and the third one we got was the one we were competing with to detect gravitational waves. We won by a couple of years, but they basically made it work well enough that they helped us triangulate.
Is that Virgo?
Virgo, yeah, Virgo. And so adding Virgo was absolutely essential to get to a small enough place in the sky that we could point to where it was and compare with.
So it's two machines in the U.S. and one in Italy, and that gives you enough data to begin to pinpoint where things happen. So now you can not only detect the gravitational wave, but actually see the electromagnetic wave from the same kind of source.
Yeah. And that one had, I'm going to skip on because I'm going to be out of your time in a few minutes, probably. You're going to kick me off. But
we're having a good time. We're having a good time.
Okay. But that had a feature, which I'll say in words and not show you the pretty graphs, but that people have explained phenomenologically what happens when two neutron stars come together. Different models. And the model that's called a kilonova was the model that fits the data very well when we look at all the different frequencies down to the radio on the signal from this neutron star merger. And that has a feature that helps us explain something, maybe. One observation doesn't do it, but one, I think, embarrassment for physics that I knew about is that we have a really hard time explaining how when the Earth was created, the heavy elements got there, like gold and platinum. Where'd they come from?
Yep.
And because the universe is made out of hydrogen and helium, and then we have stars, and the stars work by fusion, and the fusion process eventually burns out, and gravity causes them to collapse. But in that whole process, you get up to maybe iron, but not up to gold and platinum. So where did gold and platinum come from? Well, in terms of making the periodic table, we know that what people did typically is take neutrons and scatter them off some heavy element and make a heavier one and name it. And we've learned what the periodic table is, but that's making them, not in nature. And it turns out that if you take these kind of neutron star collisions, which now we know exist, they're very much like neutrons scattering in a lab to make them that they are very likely, we can't tell really on one event very quantitatively, the source of the heavy materials like gold and platinum that are in the Earth. So what we observed is probably the answer to a long question that we've had in physics.
And so you found, if I don't remember the exact numbers, but on these neutron star collisions, you can create many times the mass of the Earth in gold
Yeah, if we show slide 11, it dramatically shows it.
Oh, you do? Yeah, if we can bring up slide 11, love to. What is the number? How many?
I wrote it on there. It's hundreds of Earth masses. I think here it comes.
Yeah, 100 masses of gold.
100 Earth masses in that one collision.
Wow.
Okay, and so of course that didn't contribute to the Earth, but
sure.
Ones in the past, you can imagine some of that got into the Earth.
So it's a rethinking of the way in which the elements formed. Usually, just thinking of them as stars as nuclear furnaces, but now the collisions between these neutron stars may be a dominant way certain of these elements are formed.
Exactly, and we need more data, and there's also some unknowns in there because there's some nuclear physics that's rather complicated that goes into that.
So anyway, where do you think this is all headed then? So
that's what I'm going to show you. So I want to show you where we are today, and I'll hint at where we'll be tomorrow. Okay.
Great. Yep.
So I'll tell you what we're doing absolutely today when I'm not busy talking to you.
Yep.
If we go to slide 13. Okay, slide 13 basically shows everything we've done before the pandemic turned us off.
Okay.
Okay, and so it goes, and what it is a plot of the number of observed events up the side, and time on the axis. And the way we do things is we ran, those are O1, O2, O3 means observational run 1, observational run 2, observational run 3. Yep. And the way we run is we run, and then, as I said, because we're not limited by nature, we put in a bunch of upgrades and changes, maybe improved laser or improved optics or something. And then we run again for some period of time. And then we turn off and we lick our wounds and we run again. And so we've had 3 runs. And you can see that in the first run, we saw actually 3 events, the 2 that I talked about before, and then another one. Then we made some improvements and we saw 8 events in our second run. And in the run that we just terminated, we ran for, I think, 50 weeks. We were going to run 1 year, but we turned off slightly early, and we saw 56 events. So we're down to 1 a week.
1 a week.
The improvements that we're making now, when we turn back on, which should have been about a year from now, but are going to be maybe a year from this last summer, but they're going to be longer because it's just difficult to do the work we have to do and keep people at a distance and all the things we're having to do now. Yep. So maybe a little bit longer. But what else? So it will be better by being able to get an event a day or so. Where does that take us, by the way? It just sounds
very quickly. One quick thing on that. On the 67, what fraction of those are black hole mergers?
90%.
90%. Okay.
Yeah, I'm going to show some differences now. Okay. So as kind of the last thing that I prepared, and so let me say 2 things. One is we're working toward 04, 05, and future detectors. And as I said, we're not limited. We're limited maybe by money and making it all work, but this will continue to get to be a better story. So you can do these things much more accurately when you think about it in the future. But if we look at the next slide, it's really where we are today. So we've taken these 67 events that we have, and we've identified not the ones that are black holes, which gives us more statistics, but the ones that we call exceptional events. That is the ones that look strange. This is fun. It's of course small statistics, but it gives us some sense of things. So I'll just show you 2 examples already. We got a handful of these, and that's the non-90%. First, we've seen black holes collide, and we've seen neutron stars collide. What I show on this plot is when neutron stars collide, they should be in the distribution on the left. They are thought to be a certain range. And black holes, when they collide, should be basically off the scale to the right, that you can't be that light and have enough gravity to be a black hole. So there's a lower limit on a black hole of 3 to 5 times somewhere in that ballpark, the mass of our sun.
Yep.
Well, we found events that are in between. So what does that mean? Does that mean maybe our measurements aren't good enough? Maybe. I can't tell yet. But here's an event that's 5 sigma above where we think a neutron star should be, one of the items and well below what it would be for a black hole. So what is it? Maybe it's new, maybe it's not. But these are fun, so it's fun to play with these.
Yeah, fantastic.
If we look at the next slide, it shows, I think the next slide is...
this one here, Barry?
Yeah. Okay, so now this is the next thing we've seen. This is amazing. This we just brought out a couple of weeks ago and had a little news conference and stuff. Notice it looks different than the ringing that we saw before get bigger and bigger. It looks like just an oscillation. This is an amazing event. It's two very heavy black, if it's this, we don't know, two very heavy black holes combining and making a combined mass of about 150 times the mass of our sun. That's thought to be a region that we can't explain why there would be black holes there. That is a region of more than 100 solar masses. We believe these black holes, we don't believe. The best story for where these black holes that we've detected come from is always the fact that they came as the final products of the collapse of a star. And you make a black hole that way. But we're not sure. They may have been primordial or something else, but we think it's hard to make black holes that are too heavy. Here we see something that's very heavy, too heavy to explain, so we're not sure. The very next slide, I compare it.
Just to clarify that, so I gather, just going back to my own memory of this stuff. So if the progenitor star is too big, then when it undergoes the collapse, it actually just blows itself up.
Yeah,
exactly. The black hole left.
It's just too unstable if it gets. And right. And we don't know exactly where that is, but we're well beyond where even seeing the heavy ones we've seen, it's very uncomfortable.
Like 65 or so solar masses is usually the limit that people talk about.
Yeah, exactly. And here we started with ones that are heavier than that and make something that's 100 and something. So we're talking about black holes that are considerably heavier.
Could these black holes have formed from a sequence of mergers of?
So that's interesting. So that would mean they were created very early.
In
the universe, and in a region where there's enough of them around that they did that, or they're primordial. That's why I'm saying the picture of where these came from is the next studies that we have to do. To do that, you'd really like to get to cosmological distances so that you can see how many are there early, far out, so forth. And that's what we'll be able to do with more sensitivity. It's not so much more events like doing the Higgs, but being able to become more, everything we do now is very, not very much redshift. So it's very much non-cosmological. And the big step in a future detector, I think, is to do cosmology with gravitational waves.
And for
anyway, if you look at this if we look at this slide, this next slide, let me just say it for a minute. Then this shows this one that we see these in between. These show two merging and making the next one. The left scale is the mass, and this is this strange event that we saw. When I look at this funny shape, we can compare it with this ring down shape on the bottom, and it's at the limit of where we can detect anything because it's very low frequency. So we only see this last piece. So where I drew the arrow, it points to something that looks like that top picture, if that's really the picture. We can't fit it in the way we did the earlier ones to Einstein's equations. We're just seeing this shape. And so maybe this is a heavy black hole and that's what we're seeing, or maybe it's something else. So we don't know. And so right now we're in this kind of fun, at least I think it's a fun game, which is looking at the peculiar events that we have. Some of them may pan out to be new and interesting science, and some maybe will fade away. I don't know.
Well, look, I mean, if you can find a deviation from general relativity, all we've heard for the last 100 years is Einstein works. Einstein works. Everything that came out of general relativity was perfectly matched through observations. And if you can find the first example that stands outside that theoretical framework requiring some modification, wow, that would be
I agree. And eventually we have to do quantum gravity anyway, so we have to get beyond classical gravity.
Yeah, no, if you could find a way to test ideas like string theory with gravitational waves, how fun would that be?
Yeah, exactly. I think we have to go to black holes to do that, probably.
Yeah, no doubt. There are a couple non-physics questions I wanted to end with, but let me make sure. Is there any other physics stuff that you want to cover before?
I think we're pretty much up to date. We're busy. The last thing is we're busy actually conceiving of what a future gravitational wave detector would look like.
Yeah.
So we can keep improving LIGO for the next decade. And then we want to make one that's bigger and better. We're talking about 40 kilometers on an arm. The Europeans are talking about going deep underground. We're talking about making them cryogenic, so they're cool and quiet. There's a lot of ideas that would be
40 kilometers, that'd be 10 times LIGO, right?
Yeah, the European one is the one that I have in the slide here. And it has a lot of things that we don't do yet. So you can see there's a lot of room for making big steps. They talk about going underground. That's much quieter. Yeah. They talk about using a triangle. That's has the advantage that you can run beams both clockwise and counterclockwise and do all kinds of cancellations, which give sensitivity. We talk about going to cold temperatures. That's a hard problem, but doable. And making it specialized in certain frequency bands. So this just gives a sense, without going into many detail, that you can envision how to make much, much more sensitive detectors as we project, into the
best of all worlds. What sort of time frame would you imagine to build something like that?
We're trying to work, forgetting about governments and money and so forth for a minute. I think technically we'd like to have it on the same time frame as they do a serious space experiment, which looks at a different frequency band, so we can correlate those. And that's called LISA, and it's supposed to fly in about 2034. 2034. So in the period of the mid 2030s, we would like to have the best possible Earth-bound detector as well. Fantastic.
So this has been incredibly fascinating. There are two things that I just wanted to touch on before we finish here. One is you're talking about work that has required a tremendous amount of international collaboration to work. You talked about postdoc in Germany who found the signal. You talked about the detector in Italy, Virgo, that allows us to now triangulate the signals and so forth. We have been passing through an unusual political era in which our standing in the world has changed because of the kinds of decisions that our government has been making. Have you felt any of the impact of that in the international collaborations that are central to the work that you guys have been doing?
Well, I think the biggest impact right now, immediately at this point, is China. And that's on a very individual basis. We have a lot of very, very good students and postdocs in the US that have come from China. They have visa problems now. And so, and this now crosses not just gravitational waves, but I think physics and science in general, the extra problem of the Chinese and the attitude toward the Chinese. The problems otherwise, which is an attitude that's changed, that's more domestic, hasn't directly affected us in LIGO, where our international collaboration proceeds fine. We're stuck by a pandemic, having to use Zoom instead of meet together physically. When we, again, try to divide up responsibilities to build, we're not in a stage where we're building big things. The next steps in LIGO actually have collaboration and hardware that's being brought from Australia and the UK. As far as we can tell, we're not suffering yet from the restrictions of that. So personally, LIGO, we're not affected except for our students, postdocs, stuff like that. But I think in general for the future, it'll get to us just like it gets to anybody that's using any of the collaborations that rely on combined facilities. And it's just, look, science doesn't have boundaries. It's not a national problem. It's a universal problem. We all talk the same language, whether it's you about entanglement or I came on, or me about this. It's a universal problem. We don't have boundaries, and they're artificial. When they're made, we scientists have been pretty good at trying to work around them. It's better if we can solve them and try to work together.
Absolutely. So final thing, just to take us back to the very first thing that we spoke about, you noted that when you were 15, you were given Moby Dick. it wasn't the right book for you at that moment and kind of had this impact on your life. Now, it was ultimately a good impact. You've done quite well with yourself, obviously.
Yeah.
But when you think about kids who have some excitement about science per se, and in the classroom, they may not be getting the kind of stimulation that will make them want to pursue that further. Any thoughts, advice for young kids in that situation?
Yeah, I escaped a big problem, and you escaped a big problem, and that is that when you take kids at the age of 5 to 10 or whatever, and you see them, they're incredibly curious about everything around them. They ask you questions. They're a pest because they ask you too many questions, a young kid. And somehow in schooling, we kill that for the most part. Yep. We even have an expression called curiosity killed the cat, which to me is the problem and says curiosity is a bad thing. Curiosity is the absolute heart of the audience that you have asking you questions. It's the heart of why I'm doing science, why you're doing science. And we somehow managed to not be able to do a little math and so forth and be able to do this, but that we somehow escaped having curiosity killed. I mean, if you ask what drives me the most, it's curiosity.
Yeah.
And we use the term curiosity-driven research, but it doesn't matter whether you're doing something that's maybe more directed than you or I do. But I think the big thing is curiosity, and the people that your audience is people that are curious. Keep it up. Try to answer those questions and let it drive your life. It's a wonderful human attribute, and we've done it wrong in school, where we've kind of dissuaded you from having curiosity and asking the questions and beating away at it. And so my feeling is I managed to escape that. You managed to escape the problem. And I encourage your audience to not let curiosity kill the cat be something that runs their lives.
Yeah, absolutely. It's funny. I've never thought of that phrase literally, but as you think about it, you recognize, just as you said, it's such a bad phrase. It's the wrong connotation on creativity. Creativity is what makes us who we are.
Yeah, absolutely.
So absolutely agree with that. But thank you, Barry, so much for taking the time out.
Thank you for having me
with us. And it's always a pleasure talking to you. I hope our paths will cross in the real world.
Yeah, hopefully in New York City.
Yeah, that would be great. So anyway, thanks a lot, and we will be in touch. We so appreciate you joining us.
Hello to your wife.
I will do that. It's Tracy, who was probably listening right now. So thank you very much. Talk soon. Bye. All right, everybody. That was Barry Barish, Nobel laureate in physics for the LIGO experiment, the first direct detection of gravitational waves, an incredible achievement. And we heard directly from him the journey that took him from 15-year-old boy putting down Moby Dick, turning to science, and then making this great breakthrough, confirming Einstein's ideas, and now possibly being part of work that will take us beyond Einstein. The events that Barry's talking about at the end that don't seem to fit in directly to the general relativity paradigm. Maybe it's a measurement era, maybe with refinement, everything that Einstein said will work, but how amazing would it be if that proves not to be the case? Okay, anyway, let's now turn to a few questions before we wrap it up for today. And I believe that I can, it's big enough text that I can read what's happening over here. So again, any questions on any of that, what we discussed, happy to go a little bit further. If you want to go in a different direction, that's okay too. Anonymous Swimmer asks, question for Brian, if time is just another dimension of space-time, then why does dark energy only act to push apart space? Does dark energy also create time? That is a good question. I'm not exactly sure what the best approach to answering that question is, but let me put it this way. So dark energy is energy that fills space through time. So at any given moment of time, we imagine that dark energy is filling a region of space, maybe filling all of space. And in that context, dark energy gives rise to a repulsive gravity that pushes space outward and thereby creates more space that will exist at a later moment in time. So we are doing a slicing of space-time into space at moments of time in the description that we give when we talk about repulsive gravity driving the expansion of space. So it isn't that dark energy isn't creating more time. there is time that is part of our description. It's just that the way in which space changes through time is the operative quantity that we use to talk about the expansion of the universe, the expansion of space. And that language immediately does a separation between space and time. So there is a deep connection between space and time. As you noted, we call it space-time. But in this description of an expanding universe, we are looking at space at successive moments in time. So it's a very particular slicing of the whole space-time loaf into all of space at a given moment in time. And that's the description that we typically use. But yes, fundamentally, it is all deeply connected. Let's see. Tanzumul asks, is it possible to trap a photon, or a photon can only exist at the speed of light? Yeah, you can trap photons. In principle, you can imagine putting a photon in a cage that has mirrors, and then photon is just bouncing around. Anytime the photon is between the edges of the cage, it's traveling at the speed of light, it hits the mirror, and then you should really think about what happens when light reflects off of a mirror microscopically. Photon is absorbed and re-emitted, but the photon speed within the cavity will always be equal to the speed of light. So the answer is somewhat in between the two ideas that you mentioned. There's a LIGO question for Barry. Barry's gone. I wonder if I am so bold as to read the question and try to address it. I may not be able to address it. What is the physical limit of how we can measure the expansion rate of the universe? And its changes from the Big Bang to now using LIGO or better detector. I don't really know LIGO's role in those kinds of measurements, but those kinds of measurements are being actively pursued. They've been pursued for decades. You know, even in some sense, Edwin Hubble's initial observations of receding galaxies, by looking at the spectra of the receding galaxies, you know how fast they're moving away. If you have some means of measuring their distance, then you know what their speed was at a given distance. And that's what we mean by the expansion rate of the universe, right? When we talk about the expansion rate of the universe, we don't just give a speed. We give a speed at a given spatial separation, because the further apart things are, the faster they recede from each other. More space moving apart means that the objects themselves will move apart more quickly. So the number that we often quote is something on the order of 70 kilometers per second per megaparsec, right? Megaparsec, parsec about 3 light years, megaparsec about 3 million light years. So at a distance of roughly 3 million light years, things are receding at about 70 kilometers per second. And people are trying to refine those measurements, and there were long time arguments. Is the Hubble parameter 68 kilometers per second per megaparsec? Is it 72 kilometers per second per megaparsec? Now people are still using more refined measurements, having some arguments over the exact value, but I don't know that LIGO as yet is a deep part of that particular measurement. But if Barry here, he might give a different answer. That's my answer, not Barry's, unfortunately. Philip asks, right now I am sure we are able to create a black hole. First, we need a universe to be able to create a black hole. We have all the technology now to make that happen. Well, yeah, in principle, we could make black holes. In fact, some of you may know that the Large Hadron Collider, the machine that superseded the Superconducting Super Collider that Barry Barish was deeply involved in Texas, there was a legal suit. An injunction was issued, in fact, to not turn on the Large Hadron Collider for fear that the Large Hadron Collider would create black holes through the collisions of particles, because black holes can be any size. So Barry was talking about that first detection of gravitational waves involving black holes that were about 30 times the mass of the sun, right? And then he was talking about these outlier events where the black holes were like beyond 65 solar masses, 70, 80 solar masses coming together to yield a combined black hole of 100, 150 solar masses. But, if you take anything in the world at all, you take an orange and you squeeze it down to a sufficiently small size, you will have a black hole with the weight, not of the sun, but of an orange, right? Einstein doesn't declare that there's a minimum mass necessary in principle if you have a mechanism to squeeze things down to a very small size. So the thought was that at the Large Hadron Collider, as protons collide with each other, you're cramming a lot of mass into a very small size. Maybe you will create a black hole. Now, some people worried about creating a black hole. After all, black holes have this reputation for pulling everything in, sucking in the world around them. The fact of the matter is, black holes actually don't suck in things more powerfully than any other object of the same mass. So if you have a solar mass black hole and the sun, they both suck things in with the same gravitational pull. The only difference is you can get closer to the edge of a black hole. That is, you can get closer to the center compared to getting close to the center of the sun, because the surface of the sun gets in your way. A black hole is so much smaller that you can approach the source of the gravity at a closer distance. That's really the only difference between them. So if you create a black hole that has, a mass of a few protons, maybe you shouldn't really worry about it. In fact, the math also shows that they would disintegrate really quickly. I guess the worry was that that little black hole would pull in more material in a kind of snowball effect. Maybe it would suck in Geneva. And after you suck in Geneva, maybe you pull in the rest of the world. This was the worry. And it's not silly to worry about these things. If you're going to build a machine that probes a new energy domain, you better make sure that you're not going to destroy the universe in the process. I'm all for that. I'm conservative when it comes to destroying the universe, not cavalier. But it isn't a worry, as it turns out. The machine's been running for a long time. The universe is still here. But you're right that in principle, we could have created a black hole. In fact, had we created a black hole, it would have been incredibly exciting, to answer Philip's question, if that was the name of the questioner. And unfortunately, we've not created any black holes at the Large Hadron Collider. That's unfortunate, because how spectacular would it have been to slam protons together, create a little black hole that then evaporates by Hawking radiation, giving off the radiation that Stephen Hawking mathematically discovered should happen when you have a black hole. How great would that have been? It hasn't happened. So rather than it being something to worry about, some people were. Again, I'm not denigrating the worry, but once the calculations show that you shouldn't worry about it, you should shift your energy that's going into anxiety into energy that goes into excitement. And indeed, it would have been exciting, but as yet, we have not seen any evidence of black holes at the Large Hadron Collider. All right, a few more questions here before we call it a day. What do we have here? So Homer asks, you always say, I guess you as me, you always say that distant points diverge, move apart greatly in time on the space-time loaf when one of them is moving. Any practical example to measure that? Well, yeah, absolutely. Right? I mean, you may have followed the work of the Nobel Prize winning astronomers Saul Perlmutter and Adam Rees, who is part of our conversation here. We should have Saul part of this conversation too. I think you would enjoy listening to him. Brian Schmidt in Australia, the third member of the consortium that received the 2011 Nobel Prize. What did they win the Nobel Prize for? Doing exactly what you're asking. They used supernova, powerful stellar explosions happening in distant galaxies. The explosions are so powerful that you can see the light from the explosion clear across the universe, okay? So these are stellar beacons out there in space. And by carefully measuring the properties of the supernova explosions, the astronomers were able to measure their speed of recession and their distance. And indeed, they found, number one, that these distant stars in these distant galaxies are receding from us in exactly the way that you recount in your question. They're diverging from us. They're receding from us at a speed that's proportional to how far away they are from us. Good. But they also found that the rate at which they are receding is speeding up over time, not speeding up because they're farther away. At a given distance, the expansion rate is getting larger. The Hubble parameter is getting bigger in time. And that's the so-called accelerated expansion of the universe, which was the big shock in the late 1990s. We're still feeling the reverberations of that shock as we try to come up with refined explanations of why space is accelerating in its expansion. Dark energy, which was mentioned earlier, that's our best explanation today. But where did the dark energy come from, and why does it have the particular value that it does? Could it be, in fact, that the strength of the dark energy might grow energetically in time? What would that mean? That would mean that not only are things rushing away ever more quickly, but they would continue to do so at an ever greater speed on into the future. And if that were the case, then we might be facing what's known as the big rip. It could be that in the far future, the expansion rate of space is so high that material structures, planets, stars, people, atoms, they themselves might be blown apart by the expansion of space within them. That's one possible end to the universe. And it all comes from careful measurements of exactly what you were asking about in the question, Homer, points in space diverging through explicit measurements, determining how quickly they're diverging, how quickly they are moving apart from themselves, from other objects in space, I should say. Okay. Ernest says, do you trust relativity? I don't even know what that means, Ernest. I mean, do I believe that the general theory of relativity has been observationally and experimentally established to be an accurate description of the world? Yes, I do. It's not a question of trust. I know we're just talking informally, so I don't mean to come down on you for that language. But the reason why I have confidence is the real word that I'd use. I've got confidence in the general theory of relativity because the math of general relativity makes predictions about the world. We go out and measure the world, and the predictions are borne out. And our conversation with Barry Barish is the pinnacle example of that. Einstein writes papers on gravitational waves back in 1916, 1918. He himself was not really convinced. As Barry noted, 1930s, he wrote papers that began to show that he was not convinced that these things would be real. But other scientists, as Barry mentioned, in the 1950s, came to the conclusion that these really are a mathematical prediction of the general theory of relativity. And then people like Joe Weber and people then who take the torch in a far more productive direction to build LIGO and advanced LIGO, they find the gravitational waves. They find what the math predicts. If you've never had the experience of doing a little calculation and then looking out into the world and seeing that the world follows the pattern articulated in the mathematics, I encourage you to try to have that experience. It can be a very simple one, just a ball rolling down an inclined plane if you want. Do the mathematical calculation and then just measure the ball rolling down. And the fact that the motion of the ball agrees with your mathematical calculation, it's really thrilling. Now, imagine that happening with something that nobody previously had ever seen happen in the world. We've all seen balls roll down inclined planes, but no one before the first observation of a black hole had seen a black hole. No one before the first detection of gravitational waves had seen a gravitational wave. So it's a miraculous thing that the mathematics is able to make these predictions about the external world, and then we're able to confirm them. So that's not trust. It's confidence coming from a mountain of experimental evidence. That's why these ideas hold sway in the field. Okay, so Ernesto, so fear make mind expanded the black hole and we don't need another never-ending story collapse to la nada. Ernesto? I'm sorry, man. I have no idea what that means. I know what nada means. That's another way of saying nothing, I think. But Ernesto, if there was some hidden message in that little question, you're going to have to clarify. I've got no idea what in the world you're talking about. Okay, anyway, onwards. Jamie, how do we know for certain that the age of the universe is 13.7 billion years? Isn't it possible that the universe has been expanding at the speed of light for a long time? Yeah, so where does the number come from? 13.7, 13.8 billion years. It comes from a very simple calculation, which is this. as of today, as I've recounted, we know that space is expanding, the distant galaxies are all moving apart. So in your mind's eye, picture that film, everything rushing apart. What we can do with the mathematics of Einstein's theory is, in essence, wind the cosmic film backward. We can't literally do that, but mathematically we can do that. And as we wind the film backward, everything comes closer and closer together. Galaxies come closer and closer together. They merge, ultimately get smaller and smaller. The universe gets hotter, denser, more extreme, and we can continue winding this film all the way back to the moment when everything in the observable universe is on top of everything else, when it's all squashed together into an infinitesimal speck. And we can use our mathematical understanding of this rewind to figure out how many years we'd have to do this rewinding. And the answer that comes out of the math is about 13.8 billion years. Now, does that mean that the universe began 13.8 billion years ago? Not necessarily. The universe could have had a prehistory that we may not know anything about that led up to this compressed state from which, running the film forward, everything emanated. There could have been a long prehistory. There could have been a whole sequence of cycles, maybe, of expansions and contractions, and we're just living through the latest cycle. So when we talk about 13.8 billion years, we should qualify it by saying 13.8 billion years is the duration from when everything that we now see was on top of everything else. But whether that moment was the true beginning of time, beginning of the universe, that's the question that nobody knows the answer to. So, Jemmy, yeah, it's certainly possible that things were happening for a long time before that, if even the notion of before, which is a temporal notion, does that even make sense? Could it be that time itself came into existence with the expansion, with the Big Bang, and therefore this earlier era, we're biased into thinking in temporal language, but maybe temporal language is not even the right language to talk about it. That's a possibility too. Okay, so what do we have? A few more. What time is it now? It's almost 5 o'clock, so I'll wrap up in a few minutes. As I'm quite hungry today. I need something to eat. All right, so what do we have? 11 music. Do you think there could be ancient civilizations that we have no record of because they are millions and millions of years ago, civilization that went extinct? Yeah, it's certainly possible. It's hard to rule things out. I mean, when you look at the archaeological record, there seems to be a fairly nice progression in terms of the physiological development that we can plot out on the, cadograms, whatever they're called, but you can actually see speciation happening. So, humans or humanoid-like entities, our history goes back generously a couple million years. It could be millions and millions of years before that there were civilizations, conceivably. What's, if you want to go into those kind of crazy, well, not crazy, if you want to go into those far out speculative ideas, you can say, were we visited by some alien species that may have taken a look at planet Earth and said, yeah, they're up to single-celled organisms, or, they're up to, amphibians, whatever, but we're not that interested in hanging around because there's nobody to talk to yet here on planet Earth. Could that have happened? It could have happened. I've seen no evidence that has happened, so don't get me wrong. I'm not one of the people that talks about Area 51 in Nevada, okay? These kinds of things do not excite my curiosity at all. But that doesn't mean that there couldn't have been these kinds of visitations in the ancient past. It just means that we don't have any evidence that it happened. Okay, what do we have here? Ernesto tried again. What I said is that when I have fear of fail, the thoughts of my brother and sisters make expand the black hole because all of us are increasing the vacuum. Boy, it's a little clearer, Ernesto, but I'm still having a little trouble. Sorry, I'm just not sure what to make of that, Ernesto. I know that we're having a bit of a communication issue here. So Alex says, yes, in answer to the previous question, Planet of the Apes, you blew it up, damn you, yes. Charlton Heston on the beach sees the half-sunken Statue of Liberty. I should have mentioned this, one of my favorite films. If you haven't seen the original Planet of the Apes, you got to see it. You know, so Charlton Heston on a planet that is ruled by apes, and it turned out that for the apes, the humans were the earlier civilization, and we ruined it. Apes took over and turned it into at least something that was still in existence. Okay, anything else that I can find here that strikes my fancy to end on here? Oh, yeah, how does this relate to twistor theory? So Roger Penrose pioneered twistor theory. It's an alternate way of analyzing gravity with a particular kind of mathematical structure that Roger invented. So I'm not going to go down that at this late time. I don't really know enough about it, frankly, to give you a good enough explanation of what it is. Avish Krasta asks, Sabine Hassenfelder talks about how string theorists get lost in math and try to get the theory to fit in. What do you think about this, and should there be a new approach? Now, look, let me put it this way. We physicists who are more theoretically inclined, we do our analysis with the language of mathematics. And we use that mathematics to powerful effect, as we have seen even here today. All of the work that Barry spoke about is within the context of the mathematical framework of Einstein's general relativity. All of the work that he alluded to in the discovery of the Higgs boson is in the framework, the mathematical framework of the standard model of particle physics, which itself makes use of the mathematical structures of gauge theories, which themselves makes use of the mathematical structures of Lie groups and Lie algebras. And if we're talking in mathematical terms, making use of vector bundles that are associated to certain principal bundles that are manufactured using the mathematical structures of differential geometry over the space-time manifold, which itself is in the mathematical language, a Hausdorff differentiable manifold with a pseudo-Riemannian metric. These are all mathematical ideas, which then we have been able as a community to shape and mold into theories of the universe, which then make mathematical predictions for things that we should find. That is the incredibly successful rhythm of physics over the last few hundred years. Mathematical ideas describing the universe, its patterns, using particular mathematical structures, going out in the world, measuring, trying to find the predictions of these mathematical ideas, and on the loop of progress, the journey of progress continues. Now, we are at an interesting phase right now because we have been so successful in our experimental ideas, especially in particle physics, that we have been encouraged to go beyond the things that we can test today with today's level of technology. So we are, as string theorists, using a lot of mathematics to analyze how the world might be. We're not lost in the mathematics. We know exactly where we are in the mathematics. However, we are certainly being guided more by the brilliant light of mathematical consistency, mathematical beauty, mathematical economy, because our experimental colleagues have not been able to shine an experimental light on the high energy scales, the short distance scales, on which the new physics of string theory and unification becomes most apparent. So we're doing what we can with the tools that we have access to. And the most powerful tool that we have access to is mathematics. So again, I would say that we're at an interesting juncture, a lot of interesting mathematical ideas on the table, a lot of people examining and analyzing those mathematical ideas to see what implications we can draw from them. Ultimately, these mathematical ideas need to confront data and observation. That's why we hope there's going to be another accelerator built. China is talking about building the next accelerator. That would give us new data. That would give us the complementary illumination from observation and experiment. That's why Barry and his many collaborators working in gravitational wave physics are talking about building this very refined version of an interferometer that might be underground in the manner that Barry was talking about, shielding it better, building a space version, LISA, of an interferometer experiment, because gravitational waves, when they get to a level of refinement that we see happening, may then be another light of illumination on the mathematics of unification and string theory. So it's all just to say that, yeah, right now, certain arenas of cutting edge physics are being driven by mathematics. It's not that we're lost in mathematics. That's so silly. It's that right now, math is playing a more dominant role until the observation and experiments are able to catch up. That is my assessment of the situation. Okay, guys, with that, I'm going to call it a day here. Please join us again. I think it's going to be next week when we'll have another one of these mixed sessions of questions and answers and conversation. Again, I'd love to hear your suggestions, and we are keeping a list of the kinds of people, not the kinds of people, the people, the names of the people that you'd like to have part of these conversations going forward. And you should also note that Barry Barish has a masterclass at World Science U. So if you want to hear more, I don't know if it's been released yet. It may be. So go check it out. If not, it will be released quite soon. I know I believe that we have scheduled a conversation with Andrea Ghez, this year's Nobel laureate in physics. That may be next week or the week after or something like that. So don't hold me to any particular date. It will be happening soon. Oh, I'm being told October 28th at noon is when we'll talk to Andrea Ghez. So that will be fun. Newly minted Nobel laureate for her work on observations of the center of the galaxy and black holes. So join us then. But we may have something between now and then. So keep an eye out. Again, if you want to follow me in particular, I'm on Twitter, on Facebook, Be Green on Twitter. You can follow the festival itself on any of its social channels. Many of you know about these events through the announcement on Twitter. So those of you who are here without that and want to be alerted to what's going on, you can join the World Science Festival newsletter, or you can also sign up for our Twitter feed as well. Okay, with that, I'm going to call it a day. Thanks for joining us, and take care till next time. So long.